Ink. Okay, so yeah, pairs of non-uniformly varying quantities. So in 9A, we're looking at like vector equations of a line, so they're uniformly varying. Non-uniformly just means we're dealing with like differing x and y components. So we'll get straight in. Do you guys know what a trebuchet is?
It's like a weird catapult.
Yeah, it's a big catapult. Yeah. Have you heard that word before? No. Have you?
Yep.
Interesting. I'll tell you a theory after. Alright, so we've got a trebuchet unloads a 500 kilogram rock at a castle. The position of the rock with regards to time is given by this equation. So we have x of t is its x coordinate with regards to t, and we have y of t, which is its vertical coordinate, its coordinate on the y-axis. 15t take 4.9t squared plus 10. Okay. Part A, find the, it's written in invisible ink, it says find the initial position of the trebuchet. So that means when time is 0, so to answer part A, what's x of 0 and what's y of 0? So x of 0 is going to be minus 5 and y of 0 will be positive 10. So its initial position is minus 5, 10. You can think of it like it's to the left and up on a hill, firing a rock at the castle. Okay, find the initial velocity vector and speed of the rock. Okay, so initial velocity vector is x dash of t, y dash of t. Okay, so when we differentiate each variable with regards to t, the derivative of x is going to be 10, and the derivative of the y component is going to be 15 to take away 9.8t. Alright, so that's the velocity vector. This is going to give us the velocity for any value of time. Notice the horizontal component stays the same, but the vertical component fluctuates with regards to time, how fast it's travelling along. So that's the first part, find the initial velocity vector and speed of the rock. So we want to know the speed when time is 0. So when time is 0, what's going on? If time is 0, like I'll put v of 0 for initial, this is its initial velocity vector, right? And speed is just the magnitude of the velocity vector. So the speed is going to be the square root of the x component squared plus the y component squared. 100, 225, 325. And then whatever unit we have, let's say meters per second. So we've got part A, part B, part C. Okay, the rock hits the castle wall when time is 3.46 seconds. So the rock is launched, it's flying, and it hits the castle wall when time is 3.4 seconds. So we're going to find x of 3.4 and y of 3.4. So we'll go, we'll put 3.4 in here, 10 times 3.4, 34, take 5, that'll be 29. And this one, we can just chuck it in the calculator. I've done it earlier. We've got 4.356. So we've got 29 and 4.356. Okay, determine the angle of impact with the horizontal when the rock hits the castle. So what's happening is it's flying, so we've launched this bullet, it's flying up and it's flying down, it's hitting the castle wall, and the position where it hits the castle wall is x is 29, y is 4.356, and that occurs when t equals 3.4 seconds. So what we want to know then is what's the velocity vector when time is 3.4 seconds? Alright, so I'm going to put 3.4 into the velocity vector, so we have the velocity of 3.4. So the horizontal component stays the same. The vertical component here is minus 18.32. So we put 3.4 here. This evaluates to minus 18.32. So what this means is when time is 3.4 seconds, it's going across at 10 meters a second and down at 18.32 meters a second. So it's going like this, across 10, down 18.32. And we're asked to find the angle of impact that it makes with the horizontal. Okay, this is the horizontal line, what's this angle in here? So this is just right angle trigonometry. O and A, inverse tan of O on top of A. And do that quickly in my head, got 1.07 radians. Okay, degrees, radians is fine, you're cool. All right, determine the maximum height of the rock. So we'll do this manually, and then I'm going to just talk about very quickly how you can graph these parametric equations on your calculator. So for the maximum height of the rock, the maximum is going to occur when the y component is maximized. So if you think, if this is the y component, I want to know when does the max occur on this? Well, remember from apps of calculus that turning points occur when the derivative function equals 0. We know y dash of t is this component, okay? So in 15, take 9.8t equals 0. We'll solve through for t. And we get, I just evaluated the distance. What time value do we get? .53. Okay, so that's the time when it's maximized. Okay, so that's the x value we have when it is maximized. And so then we want to know what's the maximum height. Well, that's what's the y component when the time is 1.53. So we're putting 1.53 as the initial y equation, and we get 21.479, 21.4 meters. Okay, so we've answered all those parts. Let's look at how we can use our calculator to graph these parametric equations. And this is something we have touched on in vectors, but here's a timely reminder. So if you go to graph mode, so you're in graph, just make sure you've deleted everything, or you don't have to, I suppose, you can do it in Y1. But what we're going to press is F3 for type, and we're going to select parametric. Okay, and in here you can type in the x component. So I'm going to type in 10t take away 5. Okay, t just pops up where your variable x would normally be. And I'm going to type in the y component, 15t take 4.9. Take 4.9t squared plus 10. Okay, and we can graph it. Now, what we want to do though is we want to restrict the value of t. So we do that in V window. So if you press Shift and V window, and right at the bottom, you've got t, theta min, max, and pitch. So have a bit of a play around with those, okay? So the minimum, so the minimum shows the lowest value of t, so we've got that set to 0. So you can see if you've got the graph of it, it looks like this, okay? And then it hits the wall when time is 3.4, we've calculated that. So we can even set the maximum to be 3.4. All right, and so if I do that, what it does is it restricts the graph over that region. So you just need to be careful when graphing parametric equations that you have an appropriate domain of t, because if you don't, it's not going to show you some part of it. Okay, so that's how we do it, but be aware of the minimum and maximum value of t here, of the restrictions we impose on it. Now pitch, okay, have a bit of a play around with pitch, and you'll see what it does. So if we set it to 1, okay, that determines how many times it calculates the trajectory. So I've got it set to 1, and what that means is it's calculating the trajectory every 1 grid unit, and so that's why it's got all those lines there, okay? If we set it to 2, it's going to calculate it every 2 units, and so that's why it looks really clunky. And so it's an approximate description of the path composed of linear equations. And so what you want is that pitch value to be quite low so that it resembles a curve, so you have a smooth trajectory. So that's in V window pitch. So I think it was initially 0.02 or something like that. But yeah, have a play around of those. Obviously, the more